So, let's see if we can fill in the blanks. Based on what we talked about last time, you maybe could do this. First sentence says, a slope field is a graphical representation of a blank equation. What kind of equation do you think we're talking about? Think back to what we did with those slope fields, like how we made them. What were we using to make them? Feel free to look back. Look at all those beautiful slope fields. Say again? A derivative, yes. So an equation that contains a derivative is also known as what kind of an equation? Say again? Differential equation. There we go. Let's try that again. There we go. Differential equation. Differential equation, like I said, simply an equation, and this is the next blank here. A differential equation is an equation that has one or more derivatives in it. They can be, maybe the variables can be separated or not, but a differential equation is what we're talking about here. And that's pretty much the whole chapter is going to be dealing with that. So, on a graph, the derivative, which is in these differential equations, the derivative is the blank. Slope, correct. The derivative is describing the slope of whatever our function is. So the slope fields that we were drawing are simply little tiny slopes at various points, right? Little tiny slopes called local linearity. We're talking about, this is the term we talked about last time, really close to one little point. We're talking about the line. Because if you think about this, maybe you've done this before, if you take any function, no matter how curvy it is, and you keep zooming in on one point, you get in one of those weird moods where you're just like, obsessed with something, you just go zoom in, zoom in, zoom in, zoom in. If you just zoom in enough times, doesn't everything, no matter how curvy it is, look like a line eventually? It eventually just looks like a line, and that's really what this local linearity is about. So, let's go ahead and flip back to the slope fields worksheet, and we'll do maybe one of these, and then we'll move on after that. So, let's check this out. Number 6 would be a good one for us to think about. I realize some of you have looked ahead a little bit. There we go. If you have not attempted this one, go ahead and try it now. I'm going to go ahead and create a little table like we did last time. We'll at least try to see some pattern going on here. Anybody see a pattern right away? There's, I think, a pretty important one immediately based on the fact that dy dx is a fraction. Say again? Just like one specific pattern. Somebody just shouted out circle. Maybe that's it. Maybe that's it. I'm looking for something a little more detailed. Because it's a fraction, negative y over x, what's going to happen or what won't happen?
It's not a circle.
She says it's not a circle. Okay. So maybe that pattern was wrong. Talk to me about a fraction. What part of a fraction is pretty restrictive? Yeah, denominator can't be. Okay, so the denominator is x. So basically whenever x is 0, it doesn't really matter what the y is. dy dx will be dne, right? Okay, so when I say x is 0, what are we talking about on the graph? The y-axis. So because the y-axis is going to contain all dne slopes, we're going to leave the y-axis blank. Please don't try to draw in some kind of a vertical little slope field there. Just leave it blank because literally dy dx does not exist. So don't put anything there. Okay. It's a fraction. Denominator is pretty important. What else is important? Thanks, Reagan. So on it this morning. So the numerator, whenever the numerator is 0, as long as the x, the denominator, isn't 0, won't dy dx always be 0? Okay. So let's see here. When I say y is 0, we're talking about the x-axis. So did you have a nice horizontal pattern right there? Skip the origin, right? Because that's part of that other pattern we looked at before, but those would maybe be some early slope fields you could put in. Beyond that, we're going to have to plot some points. I'll maybe just work quietly up here and try to see some patterns. You guys showed some pretty good and quick aptitude for this before. We'll see how we do here. So I'll just plot some points, like I said. Did you guys get that pattern going on right there? I can see why maybe you might have looked at that and thought, circle. I definitely get that. At least at that point, it looks like maybe it could be a circle.
It looks like a flower.
Oh. Oh, that sounds nice. There's a lot of symmetry going on here. Hi. Get something like that. I think I'll go one more column out each way and we'll see what it looks like.
Oh, I don't have to fill in everything.
You got something like that?
Yeah, wait, use that. And drop it into the leaf. Also, we did put in the book.
What's this starting to look like to you as far as what the solution curve would actually be? It's like 1 over x? So do you know what 1 over x actually is? Like if we were going to give it a broader name? Say again? No, it does. Like part of it looks like an exponential, but there's that whole other part, right? Yeah, it kind of looks like that. I agree. It's kind of that same kind of a curve shape to it. I hesitate to say this, but take, can you picture the graph of 1 over x in your head? Take it. Those of you that are in honors pre-calc, I might be giving you some flashbacks that might cause you to freak out a little bit. Take it and rotate it.
No.
In your brain, not on paper, in your brain. What do you see now?
I don't know.
A what? Hyperbola. It really is a rotated hyperbola. Yeah, so it's one of those conic sections. Not that we're going to do anything with that, thankfully. Yay. We're not going to be rotating anything like that. We will be rotating some stuff later on, but not conics, though.
I don't even know what that is.
Okay, so I want to take this a little bit further. I'll fill it out a little bit more here. Something like that. So, guys, girls, I want to show you one more level to this. This occasionally happens on AP tests. Occasionally happens on one of my tests. I might give you a differential equation like this and have you do a slope field and say, okay, the solution curve actually goes through a certain point. Please sketch the solution curve. So I want to give you some pointers about that. So let's say that I told you that the solution curve goes, the solution curve has the initial condition y of 1 equals 1. Okay, so I say, hey, you know what? Our solution curve goes through the point 1, comma 1. And then I would say, draw a solution curve. Draw a solution curve, like right on that graph. So let's talk about what you would do. First thing you want to do is locate the point 1, 1. And I'd say based on the scaling, I think it would be pretty reasonable for it to be right here. I put a little red dot. Does that make sense? 1, 1. Okay. So what you're going to do now is you're going to draw a curve that mimics the slope field, but only goes through that particular point. So I'll do my best. I'm just going to say my solution curve would look something like that. That make sense? So notice a couple things. I did not draw anything down here, or here, or here. I only drew it in that one specific spot. Why did I draw it in that one specific spot? Yeah, the initial condition, right? The initial condition only says 1, 1. And so I'm only going to draw it right there. It could have gone differently, though. What if, instead of my solution curve going through the point 1, 1, what if it said y of 1 equals negative 1? Like that. So I'm no longer going through the point 1, 1. I'm going through the point 1, negative 1. Well, that, of course, is right here. And so instead of drawing it up in that first quadrant, I would draw this something like that. So when you draw a solution curve, try to only hit the point that represents the initial condition and no other points, and then just mimic the slopes in that particular area as you move across the graph. Make sense? Okay, good deal. Any questions? All right, well, let's go ahead and take a look back at the notes. We're going to look a little bit at Euler's method here today, and we'll see how we do where we're at with time here. But so far, so good? Warmed up? Okay. All right, so Euler's method. This is what we finished with last time. I'll give you a little preview of it. Euler's method is simply a graphical, but more particularly a numerical way of approximating a solution to a differential equation. Honestly, all this really is, we're going to be plotting points. And if you can remember y equals mx plus b, you're going to be able to plot those points pretty easily. I'll show you. I know that stuff down at the bottom of the page is a little intimidating looking. We'll kind of break it down into what it really is. So let's just go through a couple of basics here. So you'll be given a couple things here. You'll be given a differential equation like y prime equals f of xy. And the xy just indicates that the derivative, y prime, could be expressed in terms of x or y or both. Right? It could be both of them, really, like the slope field we just did. So you'll be given that information. You'll also be given a point. You'll be given an initial condition, a point that's actually on the particular solution, as well as a small, what we call step value. Step value is usually represented by the letter h, although it could really be represented by almost anything. So what we're going to do is we are going to basically be plotting points based on local linearity, plotting points based on just little tiny tangent line segments. We're going to be starting at that given point, the particular solution goes through, and then we'll use our little steps to find the other points. Really all it is. So here's the process. I'm going to show you kind of a way to organize yourself. I usually just have a column for x's. I usually start off with x0, x1, x2, x3, x4, however many I need. And then on the right side, I just have my y's. So y1, y0, y1, y2, ... all the way over to what I need to get to. And we'll talk about how you know when you're done in a second. But I want you to notice this right here. Compare it to this. Y equals mx plus b. Now we are talking about tangent line segments. And so y equals mx plus b is one way of describing a line, isn't it? I want you to notice that's all this really is. This right here, y0, that's your b, essentially, right? That's your previous y coordinate. Okay? And then this right here, this f of x0, y0, that is the slope based on the previous point, the slope of the curve from the previous point. And then h is a little tiny change in x. It's a little step size, little tiny change in x, and so that's your x, essentially. So it's y equals mx plus the previous point. We'll get some repetition with this. Hopefully you'll get into a rhythm, and it'll be hopefully pretty straightforward for you. So I think we got two examples. Let's check those out. Number one, example number one. This says, use 4 steps to estimate y of 0.2 if y prime equals x plus y, y of 0 equals 2, and h equals 0.05. Let's break this down and talk about what we're given. I'll start here in the middle. What is this right here? What kind of a thing is that? It's a derivative, right? And it's an equation, though, right? So what do we call an equation that's got derivatives in it? It's a differential equation. So I've given you the differential equation, which will give us ideas and information about our slopes, right? Yeah? Okay. H equals 0.05. That's the step size. That's the little x increment that will go as we go across our page. What about this one right here? Y of 0 equals 2. What's that? Initial condition. So yeah, y of 0, that's equals 2. That's the point that's actually on the solution curve. That's the only point that we know about right now. We're going to try to generate other points that will approximate the solution curve using little tiny line segments. And then finally, what's that? Y of 0.2. Yeah, we're trying to find that, right? That's our objective. All right, so we're always going to start at the initial condition. So the initial condition is y of 0 equals 2. And so I'm going to create my little columns like I was talking about earlier. And I'm going to say, I'll go with this. I'll go x0, x1, x2. We'll see where we're at here with x3. So x0 should be the x-coordinate from the initial condition, which in this case is?
2.
No, that's the y-coordinate.
0.2.
Nope.
0.
0. So x0 will always be the x-coordinate of the initial condition. So y of 0 equals 2. That means when x is 0, y is 2. So there we go. x1, the x's are always the easiest part. x1 will simply be the initial condition plus the step size. So 0 plus 0.05 is 0.05, right? Okay, so 0.05. And then x2 would just be x1 plus the step size. So it's 0.05 plus 0.05? 0.1. x3 would then be 0.15. And then my final one, x4, would be 0.2. How do I know that that's my final one? I'm not at the initial condition. I'm actually at my objective, aren't I? Because I want y of 0.2. And so when I get to x equals 0.2, or yeah, 0.2, then I've reached at least the x-coordinate for my objective. So the x's should be super easy. Just go plus step size, plus step size, plus step size until you get to your objective. Now the y's, a little tougher. The first one's not though. y0 is simply the y-coordinate for the initial condition. So y0 is going to be 2, right? So when x is 0, y is 2. And then I'm just going to fill in the rest here, but we're going to have to do a little work to get these. The work we got to do is basically y equals b plus mx, or mx plus b. So here's how this works. Future y-coordinates are simply based on the previous set of information. So, like I said, it's just b plus mx, and so y1 is going to equal the previous y-coordinate. So in this case, that would be 2 plus your step size, which is 0.05, times the slope at the previous point. So the previous point was 0, 2, and here's where your differential equation comes into play. You know your slope is y prime equals x plus y. So for this x1, y1, the slope based on the previous point would be 0 plus 2, right? So 2. So I'm going to write this right here. I'm going to actually simplify this just a little bit so I can use it in future steps. What's 2 plus 0.05 times 2? 2.1. So honestly, if you can do that, and you have a calculator, you can do all the rest. So let's keep going. You'll get some repetition here. Okay, so y2 is going to be based on just the most immediate previous point. So y2 is going to equal the previous y-coordinate, which is what? 2.1 plus the step size times the slope at the previous point. So the previous point was 0.05, comma 2.1, right? So what would be the slope based on that previous point? 2.15. I'm getting my slopes from my differential equation. Just to basically 2.1 plus 0.05. Okay, so use your calculators here. The numbers are starting to get less pleasant. Let's figure out what y2 is actually in simplified form. We're doing that simply so we can use it again in a future step. All right, any answers on that one? Y2 equals what? 2.2075? We agree? Okay. So 2.2075. Thankfully, we just got two more to go. I think you can see these decimals have the potentially to lengthen out significantly. So let me pause right here, though. Do you have any questions? Is this making sense to you? Are you seeing where we're getting our slopes? Mackenzie, you look like maybe you've got something to say. Not yet? No?
I'll figure it out.
Are you sure? So no questions. You're just still trying to process a little bit. Okay, fair enough. Let me know if you do. All right, so Y3 is going to be based on just the most immediate previous point. So Y3 will equal the previous Y coordinate. So that would be 2.2075 plus the step size, which is 0.05, times the slope based on the most immediate previous point. So let's see here. Since slope is equal to x plus y, this one's actually pretty straightforward, isn't it? 2.3075? Yeah, okay, so 2.3075. But then, of course, we've got a little arithmetic to be done. I don't know. I don't know what it is. I'll let you guys help out.
Can we round it all?
I would not round till the very, very end, simply because those intermediate roundings are going to make you be off for the next step. And we're almost to the last step here. So, okay, any solutions on that one? What'd you get? Did you multiply it out?
5.36. I rounded.
That sounds way too big.
I got 3.3612. I
I got
did.
2.3228.
What did I do?
Whoa.
Oh, I times by 0.5 instead.
Oh, that'll make a difference. So Alicia and Devin are a little closer to what I would think would be reasonable, but you guys are still differing by a pretty healthy margin there.
I got 2.3228.
I did it wrong. I got that.
2.322 something.
2.322875.
Yeah, that's what I got.
Chandler said,
Yeah.
Okay. So Alicia, it sounds like maybe the majority. See if you can figure it out. Yeah. Okay. So Devin, will you say it one more time so I can write it up here?
2.322875.
Okay. We okay with that? All right. So then our final process. Do you see how if you can do the first step, can't you do the other steps too? Of course, the numbers get a little more complicated, at least in this one, but hopefully you can still see the pattern. Okay, so then Y4 is simply the previous Y coordinate, so 2.322875 plus the step size times the slope based on the previous point. So I think the slope based on the previous point simply just x plus y based on the previous point. So I'm going to go with 2.47. 2875? Okay, so 2875. And then your final task then would be to, multiply and add and come up with something that I imagine is going to be in like the 2.4-ish range, right? So 3 decimals would be the standard, right? So rounded to 3 decimals, what do you guys think? Some of you worked a little bit ahead. 2.447. Okay. So we all in agreement on that number? Okay. So I just want to maybe remind you real quick what we just did. We took a differential equation, and honestly, this particular differential equation is one of those first-order linear differential equations. It's not something that we've talked about how to deal with, right? But we can still approximate the solution curve by plotting some points. So these points would be 0, 2. So right there, there's a point. The next one would be 0.05, 2.1. So maybe that's here. And then 0.1, 2.2075. Maybe that's there. Come on, there we go. 0.15 went up even a little bit more. And 0.2 went up even more extreme than that. I don't know, something like that. Those points that I'm attempting to plot there we go, would represent what the solution curve would actually look like. It's based on little tiny line segments, right? And I would say our step size was pretty small, wasn't it? 0.05. So this would be a reasonably good representation. You can see that the y values are definitely increasing, so this would probably be an increasing function, right? And those little line segments would give us a pretty good idea of what it looks like. Of course, if I wanted an even better picture of what it looks like, what could I do? More points, and more points would mean the step size goes smaller, right? So if your step size was 0.01, you just increased your workload by a lot, right? To go from 0 to 0.2 using just 0.01 every time, you just multiplied your workload by 5, didn't you? But that would give you a better idea of what this would actually look like. Doesn't this feel like something that if you really wanted a good idea, like a computer calculator idea, something that could run the numbers very quickly based on the pattern? This is something you could program a calculator to do. Don't get any crazy ideas, though. They usually give this to you on the no calculator part. So they want to see that you can actually demonstrate Euler's method. So, yeah, question?
So what exactly is our answer?
Good question. So our answer is simply a point. It's x comma y. So what it is, like here's your x and here's your y. All it really is we're saying that the point 0.2 comma 2.447 is our best approximation for y of 0.2. Okay, so we were never given the equation for y, right? We were given y prime. We were given the differential equation. And so what we found here, this set of points, and ultimately our final answer is a point that is close to the actual value of the curve at that x value. So it's an approximation. It's approximating the value of the curve based on little tiny line segments. So, yeah. So all about approximation on this, which I know is a little bit of a fuzzy science, right? That's what it is. Okay, so I feel pretty good about that. Do you feel okay about that? I don't feel like we should do the next one right now and expect you to remember it for next Monday. I think what I want to do now is leave this one where it is, go over what we did yesterday, and then we'll use maybe number 2 as a review for what we did today. Right, give you a little bit of time and space to sort of kind of forget it a little bit, and then hopefully get your understanding back up to par on Monday. Make sense? Or you could practice it all weekend and have it mastered by the time you show up on Monday. Up to you. Up to you. All right, so I think that's good for today.